Hi guys, this is AP Chemistry, topic 8.4, acid-base reactions and buffers. So the objective is to be able to explain the relationship among concentrations of major species and a mixture of weak and strong acids and bases. So if you just look briefly at the essential knowledge on your handout and also in the on the slides, you'll notice you're going to have to be able to know what to do when you're reacting to different things. Can be a strong acid and a strong base, a weak acid and a strong base, a weak base and a strong acid, or a weak acid and a weak base. And you'll notice that there are certain things you need to do depending on which one is the excess reagent and all that type of stuff. So just be prepared. So if you have a strong acid and a strong base, so if you have an unequal amount of each, the limiting reagent will be neutralized, and the pH of the solution is based on whatever is left over. So what you need, this is kind of an easy one. You got to find the moles of acid and base, subtract the two, and the larger one from the smaller one. Whatever is the leftover one, that is your excess reagent, and then you need to divide the moles of that by the total volume of the solution, and you're going to find the new molarity of the solution. And from there you can get the pH. So being able to recognize what is considered a strong acid, strong base, again, heard this a lot already, but hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid, and perchloric acid. Your strong bases are metal hydroxides from group 1 and group 2, so sodium, rubidium, strontium, barium, calcium, cesium, lithium, potassium, etc. If you have a weak acid and a strong base, if the weak acid is the extra one, then you end up with something called a buffer solution. And that is a solution that contains high concentrations of some kind of acid-base pair. And the idea is that this will resist changes to the pH. Then you're going to use something called the Henderson-Hasselbalch equation to determine the pH of the resulting solution. We'll talk about buffers later on, and we're going to use this equation especially later on towards the end of our unit. If we have a strong base, and that's the one that's in excess, this is going to be similar to the strong acid or with a strong base type of thing that we did on the previous slide. So you'll get the pH from getting the molarity of the solution of the excess moles of the base, and divide those moles by the total volume of the solution. And then from there, you can figure out what the pH is, what the molarity is, etc. If you have the same moles for your weak acid and strong base, then you're going to have to do something that should look a little familiar. Use an ice diagram to find the concentration of the hydroxide group, or the hydroxide, and then find your K sub B, which is your K sub W over your K sub A to use as your K constant. But we'll see some examples for different ones in a bit. So if you have a weak base and a strong acid, so kind of like before, the weak base can be excess, so then you use a Henderson-Hasselbalch equation to get the pH. If your strong acid is excess, then you can do what you did before, where you would take the number of moles and divide it by the total volume, and from there you can get the pH and the molarity, etc. If you have a weak acid and a strong base and they're equal molar, the reaction is at its equivalence point, and the moles of the acid and base are equal. So you're going to use an ice diagram to find the equilibrium concentration of the hydronium ion, and then use your ice table eventually to establish equilibrium, etc. If you have a weak acid and weak base, the resulting solution will react to reach equilibrium and can be shown as this. Sorry, I forgot to do it a couple of slides ago. Okay, so if 100 mLs of 0.100 molar of the acetic acid is added to 100 mLs of 0.100 molar potassium hydroxide, calculate the pH. You're given the Ka of acetic acid, and it's 1.8 times 10 to the negative 5. So first you have to recognize what you have in this reaction. We have a weak acid and a strong base. So this will be some type of neutralization reaction because it's an acid and a base reacting together. So you should end up with some kind of dissolved salt and water as your products. So looking at this, your K's will be our spectator ion, so all you're left with is, well, pretty much everything else. So if you look, all your stuff, all your reactants or products are in a 1-to-1 ratio. And then you can see that it's 100 mLs times 0.1 and then 100 mLs times 0.1. So that means we have, looking at this quickly, we see that our moles of acid and base are equal molar. So it means the same. So we know that the reaction will go to completion. The reaction will then reestablish equilibrium with the weak conjugate base reacting with water. This is the basis for the ice diagram. So that means that, so I'll probably can erase a couple of these things, so I need space. So I'm going to, so just kind of keep these things on your paper, don't erase these as well. I just need the space. That's cool. So for so how you write out your ice diagram, your ice chart, if you will. So it's going to be the water reacting with the conjugate base, and then whatever is on the product side is from before. So you have your acid and your hydroxide group. So my ice diagram, you know that water doesn't factor in, so I'm actually going to kind of just use this. So my concentration for my, let's see, the concentration for my, so how do we get the, what should we call it? So how do we get the concentration for my my ion, or sorry, for my conjugate base. So it's going to be the number of moles of it, so 0.0100 moles divided by the total volume of the solution, so 0.200 liters. So my concentration of that's going to be 0.0500 molar. The other two don't exist right now. So again, when it decreases, it's going to change by x based on my stoich. The other ones will just increase by x. Since this is a base we're looking at, we need to find the K sub B. So we're going to assume that this is at 25 degrees Celsius. So the K sub B equals your KW over KA. And the Ka you're given in the problem, K sub W, it's always 1 times 10 to negative 14 if this is just regular temperature. 5.6 times 10 to the negative 10. So you're going to make this, because we're dealing with bases here, you can make this 5.6 times 10 to the negative 10 equal to the concentration of X times the concentration of X over 0.0500 minus the concentration of X. So you can use your calculators. You can see that this X, the X on the bottom, is going to be negligible. X equals 1.6 times 10 to the negative 3 molar, and this is my hydroxide concentration. So I want to find the pH of the solution, but what I can do here is I can find the pOH first. So the pOH is the negative log of this, of my X. Not my X, but the X from the problem. Actually, yes, that's but anyway, that equals 2.80. To find, oh gosh, okay. Where am I going to put this? To find the pH, though, all you need to do is subtract 14 minus 2.80, and then your pH will be, put it over here. So the pH is 14 minus 2.80 equals 11.20. All right, guys, very good. If you have any questions, please let me know. Oh, wait, no, we're not even done yet. Kidding. So that's how to get the pH. You have a weak acid and a strong base, and they're equal molar. Okay, the next problem, however, it's going to be, well, luckily for us, well, you'll see, it's actually relatively easy. What is the pH of a solution composed of 500 milliliters of 0.250 molar sodium hydroxide, NaOH, and 400 ml of 0.200 molar hydrochloric acid? So first thing you need to do is recognize if they're strong or weak, whatever is going on. And so we both know that these are, since we have both strong acid and a strong base. Okay, so they're both strong. Next step is being able to tell, is there an equal number of moles? So 0.500 liters times 0.250 moles over per liter. So we have 0.125 moles of just the hydroxide group, because I don't care about the sodium. These are in a 1-to-1 ratio, so we keep an eye out for that. If it's not, you have to adjust. 0.4000 liters times 0.200 moles per liter. And again, luckily for us, these are in a 1-to-1 ratio, so the moles of the H will equal the moles of the Cl1 minus. 0.0800 moles of the hydrogen ion. So these are not equal. So then you need to subtract these two. You'll end up with 0.045 moles of hydroxide extra. This is my excess right here. This excess will determine my pH now. So you can say that this was step one. Well, first your step one should be, what is it, weak acid, strong acid, whatever. Then determine the moles, determine the excess, get the concentration. So since we have 0.045 moles of hydroxide, divide that by my new volume, 0.9000 liters, the total liters. Let's see, what am I going to end up with? I will end up with 0.045 divided by 0.9. 0.050 molar OH. So my next step, I can take this concentration, I can convert this to POH because that's what I have. So the negative log of OH, or the negative log of 0.050, is going to be about 1.30, and that's my POH. But I want to get the pH. So my last step will be my pH equals 14 minus 1.30, which would give me 12.70 for my pH. All right, so if you have any questions, let me know about this. So for just letting you know, for your assignment, you're going to have some scenarios where you have to do the math, others where you have to know what steps you need to take to determine the pH. So make sure you refer to your notes in the video for that. So if you have any questions, let me know. Thanks.